Okay, and a good morning to everyone. And Ernie and Debbie have basically ganged up on me. Debbie found the new CD, which everybody seems to be appreciating the beat on it, and you don't have any idea who's playing what on it. Do you know the title of that one? Well, do you know the title? Ready to Go. There's some other interesting titles. That's why she was interested in it. Some real nice titles. Some of the music is, okay. It's definitely not 1970, 80 rock. So with that, yesterday we had an interruption, which we apologize for. We had tried to arrange so that would not happen. And we're assured it would not happen. So our apologies for the ineptitude demonstrated. We had an evacuation that we had to do yesterday in the middle of class. We came back, and for those of you who left, we came back and did some more presentation on the material. So we finished up some work on metric, and we finished up some work on conversions. We talked about some of the problems, so we were able to spend another 10, 15 minutes before we finished off yesterday. So with all that said, it is time for Q&A. Now, Marisol told me she had questions. Do you, hold on, Michael. I was attacked by Marisol yesterday, warning me there were questions that she had. So I'll start with you, Marisol. Start with somebody else. Now you, okay, Michael, you've been given the green light.
Number 2 from 7.4.
7.4, and is it in the book or a computer problem?
Computer problem.
Okay, a computer problem. So we're in 7.4, and this is the second of the computer problems, so that doesn't tell us anything about where it is in the book, but what is your problem? Will you give me the numbers?
0.04 kilometers.
Okay.
2 meters.
As in T-O, not T-W-O. We want to go 2 meters. Okay. And I don't mean the receiver for the X receiver for the Cowboys. So we want to go to meters. Now, in terms of this, I've been suggesting dimensional analysis. And I talked with Sarah about this last night also, because there's a question of how do you approach this. And I mentioned to you yesterday, as an engineering student, where I did metrics with physics and chemistry and the entire curriculum for lower division in those majors, just dimensional analysis seemed to be the simplest way of doing it. And there are a variety of things you can remember. That little saying that we talked about yesterday, I asked her if she'd ever heard that before. She hadn't. And so common sense and dimensional analysis would be my approach. So to that extent, I'm going to get a straight edge and set this up as a dimensional analysis problem. And so what I'm going to do is remind you that what we want at the end is what I'll start with, which is contrary-wise to what's done in the book, but we're going to do it Math 10 style. And I think that'll save us some trouble. I'm just going to use M for meters. That's not miles. And I have something with meters and kilometers or kilometers, depending on how you want to pronounce it. So if I have kilo meaning 1,000, 1,000 meters will be 1 kilometer, and I have 0.04 kilometers, and I immediately see the kilometers canceling, and I'm simply going to go ahead and multiply 1,000 times 0.04, move the decimal 3 places to the right, hence 40 meters. Okay.
1 meter equals 1,000 kilometers.
Ah, that's an interesting relationship. Michael's saying that you did what I was doing yesterday occasionally, getting trapped the same way. Because we think in terms of wanting 1 meter, and then it makes sense, well, I'll put 1,000 down below. But we forget that it's the 1,000 meters that makes the 1 kilometer, and therefore you have to be careful where you place them. Your thought was in the right spot, your motivation was in the right spot, your procedure was in the right spot. What you didn't catch was that 1,000 meters was 1 kilometer. But that's the typical process. And these are so much shorter than the 4 and 5 factor problems you had in dimensional analysis as we illustrated yesterday. out of the math 10. Okay, Kim. Oh, wait a minute. You're comparing, okay, what Kim's saying, meters is 1 and millimeters is 1,000. That may be true. 1,000 milliliters equals 1 meter. But I have what? A kilometer. The KILO is 1,000 meters. The MILLI is 1/1,000th. So remember, if it ends in an I, if it's one of those I numbers, then centa means it's 1 over 100. Milli means 1 over 1,000, not million. And we have deci, which is 1 over 10. So if it's an I, it's a fraction of a meter. So again, thinking right, but you're going to millimeters, and we had nothing here with millimeters. Okay, Marisol, your turn. 7.5. Is it a computerized problem or a text problem? Okay, would you share it with me, please? 40 degrees Celsius or centigrade? 4. Okay, so what can you tell me from yesterday? What kind of day is it? The frosty 5s, this is really cold. So 4 degrees Celsius, just above freezing. Okay, now, I mentioned yesterday I hadn't done the formula yet. There's a formula we need to talk about. That was the way we finished up just before we left yesterday. So I still need to talk about that, but can you make a conversion here common sense-wise? If frosty 5s, that means you're close to freezing, right? And what is freezing in Fahrenheit? 32, so you're going to be a little bit above 32. And remember, for every degree that you are in the metric unit, you're about 1.8 in the Fahrenheit unit. So it's about a 1.8 to 1 ratio. So this is about 7 degrees above, so I'm going to figure about 39 degrees. So you can sort of think your way through it, trying to get this sense. And remember, it was frosty 5s, tingling teens, temperate 20s, thirsty 30s, and flaming 40s. Again, the argument I'm making, you see a temperature, you don't have something wired into you that said, oh, I know how cold it's going to be. You just have a general idea. When it says 4 degrees above 0 Celsius, or about 8 degrees above freezing, you better have a coat on. So you make that judgment, right? As opposed to, it's 74 degrees. I know exactly how I'm going to feel outside. Because what gets tied together, by the way, when we name any of these temperatures, and I need to comment on that. 2 different things. One is humidity. If you have ever been in the Midwest or the East at 90 degrees, you wilt. You become a puddle. You just, no energy. Here you can go 90 degrees and work and not think about it because the humidity is so much less. Now, go to a place where there's 4 degrees above freezing with a wind chill with 40-mile-an-hour winds. That 4 degrees means nothing. You go out 4 degrees above freezing with a 40-mile-an-hour wind, and you can get frostbite from the wind and exposed surfaces. So we keep that in mind. Now, I need to go to the formula. Centigrade or Celsius, it was known as centigrade for a whole long period of time that I was involved with it. But Celsius or centigrade, it means you're doing it by 100s. So freezing is 0, boiling is 100, and you take it in between. The same difference for Fahrenheit is 180 degrees difference for the 100, hence the 1.8 ratio. Now, there are 2 formulas, and I don't know which way you want to remember it. What's fun, when I bike ride sometimes, and I had a computer on the bike that gave me a number of different readings, and it would give me a centigrade or Celsius reading. So it's nice to use that formula in your head while you're riding a bike. You have to be careful you don't hit people, but at least it's entertaining as you think through the temperature conversions. So that's where I'm headed now, and that is going to be, I just have to get to the end of the section where we were yesterday, and that was in 7.5, I guess, correct? And we have that formula. I see where it's being applied. I just need to get the formula where it's stated. so we can see it. And mercy, where is it going to be given? I'm on page 550, and I'm just trying to find where the statement of the formula is, and there it is. Conclusion, which is just before example 5, and I was expecting to see it in a block. So Fahrenheit is 9/5 Celsius plus 32. Now, 9/5 is 1.8. Think about that for a moment. 9 over 5, 1 4/5, that's 1.8. So my comment was for every degree Celsius, you have a 1.8. So let's go back to that formula. So you take 1.8 times your 4, which is going to give you 7.2, and then you have to benchmark that freezing is 32 degrees Fahrenheit, so you're going to be that 4 degrees Celsius that was above freezing, and that's what that's telling you. So each one of those is worth 1.8, and then you have to benchmark yourself back to freezing point for Fahrenheit, which is 32 degrees. So we're going to be at 39.2, I believe. Okay? So I'm going to put that, okay, that's about as good as I can hope for. Let me write the formula on the board. And whether you want to memorize it in this form, there's another form I'll look at in a moment here. Well, when you are going, okay, the question Kim's asking, will I always have 9 over 5? If I start with Celsius and go to Fahrenheit, I'll always use this formula. Now, what I want you to understand is if I solve for C, otherwise I've given you a formula in terms of F and C. Now, if I subtract 32 from both sides, then I have 9/5 C, correct? I subtracted 32 from both sides, and that's what I'm left with. Do you agree? Just stay with me for a moment. Do you agree with what I've done? Add negative 32, add negative 32. This will be 0 here if you prefer. But over here I will have F minus 32. And since the identity property for addition, this is just going to become 9/5 C. Now how do I get rid of a factor? Divide by it, right? Or multiply by its reciprocal, 5/9. So I'll multiply both sides by 5/9. And there's your other formula. Now, hint, as I've said to you yesterday, instead of memorizing a bunch of formulas, go with one and work with it. So if I'm going to look at these, this is an easier one for me to use because I know the ratio's 1.8. And so I'll just take whatever Celsius I'm given and multiply it by 1.8 and add 32. I can think my way through that and pretty well understand the formula. Now, let's say somebody gives me a Fahrenheit problem. And let's say we said yesterday that if you had 98.6, that's your what? Your usual, acceptable, normal temperature for some people. Now, some people have a normal, a little bit above that, a little bit below, but let's just take that at 98.6. I can just go ahead and say, substitute in here when F is 98.6. So I'm going to take 98.6 Fahrenheit and go to Celsius or centigrade. Well, I can use the same formula. 98.6 equals 9/5 C plus 32. So what would I do? Subtract 32 from both sides. Okay, so I'm going to have 98.6 minus 32 equals 9/5 C. And if I wanted to, I could right now say what? That 98.6 minus 32 is going to be 66.6. So I have a 66.6 equals 1.8 C. Because 9 over 5 is 1.8. So divide both sides by 1.8. So I have 66.6 divided by 1.8 equals C. And if I look at these two, I get exactly what I was talking about, because here I took my F minus my 32. Well, that's how I got the 66.6. And 5/9, this is the reciprocal, if I think of it. This was 9/5 here. So I'm dividing by 9/5, take the reciprocal and multiply. You get exactly the same answer. Now, this isn't a nice number particularly to divide, but multiplying by 5/9 isn't so hot either. So either way you're doing it, it's sort of a mess. But if I take 1.8, and this is one that's worthwhile knowing, because when you go to a doctor's office these days, oftentimes the temperature is given to you in what? Celsius, not Fahrenheit. And so I move this over 1, the usual litany here, and I'm going to add a 0. And so I take 18 into here, and this is going to go 3 times, right? And I get 54. So I subtract and get a 126. And it looks like 8 times this would be 64. It's going to be too big. So I'm going to go 7. Will that be too big? Yes, it is. 7 times 8 is 56. Oh, I'll be there. 56 and 5. And so I will have 126. So 37 degrees Celsius is what? 98.6, if I did my division there correctly. Now I should check that. 54, I subtracted. I had a 12, a 6. I brought that. I have 56. Carry a 5. 126 is 37 degrees. Now, somebody says you got a 38.5 degree temperature Celsius, then you're 1.5 above normal. If you have 40 degrees Celsius, then you have a definite temperature. That's your flaming 40s. And you're 3 degrees above. But note, you're 3 degrees above in terms of Celsius. Translates into what? You have to be a little bit cautious here when you look at these differences. Somebody says your child has a 40-degree temperature, Celsius. Is that just 3 degrees above normal in your usual thinking? It's 3 times what? 1.8. You're at 5.4 above normal. And in the 98.6, so if you think of your 98.6 plus your 5.4, you're sitting there with a 10, a 14, a 104-degree temperature Fahrenheit, and that's ice bath time. Something to get the temperature down. So you do have to be a little bit cautious when you look at these differences. So when you say, again, somebody says 40 degrees Celsius, you don't say, oh, just 3 degrees above normal. No, 5.4 above normal. Yes?
So when we're working with centigrade and Fahrenheit, we're going to set it up as an equation instead of how much?
Yes. Question is, when we work with centigrade and Fahrenheit, are we going to set it up as an equation instead of a how much? And the answer is yes. And the reason for that is you have to benchmark. You have to either subtract 32, so as we slide over here, you're either subtracting 32 from Fahrenheit or you're adding 32 to 9/5 Celsius. You can't just say it's a linear relationship. So you can't do it in the usual process. You have to do substitutions.
With that problem that you just did, would that be easier if we were working with fractions?
Okay, the question is, with the problem I just did, is it easier working with fractions as I would do here? Well, let me ask you this. If I play this game here, use this formula, and I take 5/9, you remember we said when we subtracted 32 from your 98.6, we got that 66.6. Now, what's your choice here? You can either divide 9 into here and multiply by 5. That would be one choice. Or you can change 5/9 to what? A decimal. But what is it as a decimal? 5/9 is a decimal. Come on. This is the shortcut. Anybody? What's 3/9 as a decimal? Reduce 3/9. Okay, it's 1/3. You get 0.3333. 6/9 as a decimal. 66666. Now the key is the 6/9 gave you 6s. The 3/9 gives you 3. So what will 5/9 give you? So much for analogical argumentation. It will give you 5s forever. 7/9 will give you 7s forever. 1/9 will give you 1s forever. So 5/9 is 5s forever. Now you're going to take 5s forever, meaning after the decimal point. 5s forever times 66.6. How many 5s are you going to use? Well, you could use 3. What's wrong with 4? What's wrong with 5? Just use 1. You're getting sloppy. Okay? So the point is, there's a sloppiness if you go to decimals here. So if you divide the 9 into here, now you can do the division, multiply by 5, but is it any easier doing that than taking 1.8 into 66.6? That's the question. In these problems, unless somebody gives you a really nice number, the fractions don't often work so well. So for example, if I come back up to here, and I say, golly, I've got Celsius at 30 degrees. Hey, I feel good. C at 30, 5 into 30 is 6, 6 times 9 is 54, add 32, 86, I'm there. Ride the bike, do it in your head. Somebody says, hey, C is 14 degrees. And I go, nah. Stop the bike, get out the paper, write it out. Not going to work doing it in my head as easily. It depends on the problem. Now, what I did get in your case about yesterday, when I returned the quizzes that we had done, and I commented on it yesterday, this knee-jerk into there is a fixed solution manner in my head. So every one of these problems I'm going to do with a fraction, or every one of them I'm going to do with a decimal, and you get yourself trapped into what I rigged as a very nice problem if you think for a moment about how to approach it. Works great, choose badly, and you get chewed up in time. So in a sense, you're asking the same kind of question. Can I just always use fractions? No. Should I always use decimals? No. Look at the problem and see what works. Make sense? Okay, so it's like saying every time I go out and run, I'm going to wear a coat. It happens to be 98 degrees outside. Go ahead. Bad choice. Look at the environment, look at what's happening, and make a choice. That's what I'm asking in the problems. And part of my concern, and let's get on this topic, because I'm riding the horse here at this point, and I want to finish it off. You've got a test coming up, folks. Good preparation. Take every quiz we've done since the last test, write it out on a piece of paper, and go through every problem and give yourself roughly 3 minutes per problem. Because I anticipate 20 problems in the test, 60 minutes. So that's 3 minutes a problem. Okay? If you're spending 6, 10 minutes a problem, you aren't ready. So you go through that time and time again until you are ready. It is not enough to understand. You have to work well. And I don't remember how many quizzes we've had since then, but let's say that we have, with this one coming up this Friday, that we might have a half a dozen quizzes. We've had sometimes 5 problems in those quizzes. So if we had 5 problems and you have 6 quizzes, there's 30 problems. I'm going to look at those quizzes when I make up the test. Very seriously. Okay, Michael.
Can you expect any different time problems?
I'd say the quizzes are going to be a very good indicator of what I'll hold you accountable for. And here is the big issue. It's that split of about 20/80 that I'm concerned about with the computerized homework. You're running about anywhere from 3/4, 75% up. Math 10 problems. And then the last third to the last 20% are the algebra problems that I'm supposed to have you ready for. I am assuming you can do the arithmetic or you wouldn't have been in here because we went through Math 10. My goal is not to test you on Math 10. My goal is to test you on the pre-algebra content. So the problems I've been giving on the quiz are that last 20% of your homework typically. And that's where you aren't putting the time in. So you need to go through every quiz problem and repeat it until you can do that problem in less than 3 minutes. If you do that much, I can't guarantee you that you'll be able to do every problem I give you. If I repeat some of them as test problems, you're certainly prepared. If I get something very similar, you're very prepared. It's not going to guarantee you that you're going to get them all done, and that's what we call a sufficiency condition. If you do this, then this will happen. Okay? If I throw water, you're going to get wet if I throw it at you, typically. So that's sort of like, if this happens, this result. But it is what we call a necessary condition, meaning if you don't practice, 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 you will not get done in 3 minutes per problem, and you will see on your test grade a quiz result or worse. Now, if I give you 5 problems and I've given you 20, 30 minutes, that's like 5 to 6 minutes a problem. I give you half that time and quadruple the number of problems in 1 hour under pressure. If you're getting a 5 on the quiz problem and you don't do anything about it, you can't expect even a 5 on the test, meaning 50%. So what has to happen here, and this was part of the discussion we had in the bridge meeting yesterday, finishing off the semester, putting things into really serious effort, meaning you can affect your grade by 1 to 2-letter grades in these last 3 weeks. We have a major test and we have a final. That is 300 points. Okay, at this point you have 2 tests. That's 200 points, quizzes and homework. You have half your grade yet in 3 weeks. Is that sobering enough? Half your grade ahead of you. So you can turn your fortunes around in serious ways, good or bad. Nobody is doing so badly that they couldn't recover, and nobody is doing so good that they're home free. This is time to really get intense. This is where you start doing stuff at home. This is where you show up on the tutorials and you give everything you've got to make it happen, or you end up repeating a course, ruining your GPA, and not doing what you're capable of doing. This was our discussion yesterday in Bridge for about 40 minutes for both groups. You went through this last semester. You know what it is to finish off. Now make it happen. Positive side. With the rare exception, such as this question, what we're doing is exactly where we've been. Dimensional analysis, but they're easier. 8.1 and 8.2. We talked about that yesterday. Percents. They aren't going to be any worse than what we've done. There's one wrinkle I want to talk about. Okay? We are skipping section 7.6 because I don't like the section. I don't think it's relevant. 8.1 and 8.2 are not bad. 7.3, 7.4, 7.5 are not bad. The only thing we're going to do that I think is going to mess with your head a little bit, we're going to trade off some problems in dimensional analysis with proportions. And I commented to you that with proportions, you're going to have a problem where you have to be careful with proportions, because with proportions, it's a way of thinking, proportional thought, which is different than the algebraic proportion where you cross-multiply. So we cross-multiply, but you have to set it up as a proportion. And I told you earlier that dimensional analysis is a way of not having to deal with proportional thought. Because under duress, what happens to your ability to do analytical thinking? It's compromised. And you want to grab Linus's blanket from Charlie Brown and go into the fetal position and not think. That's what happens under stress. Okay, so that's the story. It's the only topic I have any concern for you. So I've gone a lot further than you probably expected in this problem. Are there other questions from the homework? Okay, so we went from a lot of questions to this one helped. And maybe can finish. And I went ahead and opened up the computerized homework, I think, until the end of the week for 7.2, 7.3, 7.4, 7.5. I think everything's set up until, and if we need more time. I've learned that one thing this semester, that putting those arbitrary limits on how long is not to my best advantage nor yours. So I'm opening them up much more than I was. Okay, so any other questions on homework before we sort of push the envelope a little bit further? Kim, you have one.
On 7.2.
Okay, 7.2. This is a computerized?
It is.
Okay, so 7.2, we got a 7.4, a 7.5, and a 7.2. And I'm hoping that this is going to be roomy enough. Will you tell me the problem and I'll make the judgment?
Find the unknown length. And it's
The unknown what?
length.
Length.
It's a very, very good
It's a what?
trapezoid.
Trapezoid. Okay, we've got a trapezoid. Is it a regular trapezoid? Two similar trapezoids like we did yesterday. Okay, so we have two similar trapezoids that we did yesterday, and you're having trouble setting up the proportion?
Yeah.
Okay, do you have the picture drawn for me? Okay, Michael, do you want to hand that up here? And thank you. And we will look at the pictures. Okay, two trapezoids. One ostensibly smaller than the other. So be creative. Okay, you made them so they looked like what? Pretty close to being the same in terms of here, here. Maybe this one's a little bit shorter. But this is a length of a side, and it is compared to this side. So these are the proportional parts. So this is to this as that is to that. Take the parts that are related. So the 4.5. So I have a 4.5 here is to this 3 1/4 as 4 is to A. Now what that gives me is a proportion that has a mixed number in it, unfortunately. So I'm going to have 4.5 is to 3 1/4. So 4 1/2 is to 3 1/4. And now it's back for a moment, if you would, Ernie. As 4 inches is to what? A. Now we can come. And now I have a proportion. Now, is that part okay with you? There we're okay. Okay, now you've done the hard part. Now the question is, what are your choices here? One would just be make that left side one very nice simple fraction. So this is what? If I just focus here for a moment. 9/2 or 9 seconds or 9 halves over 13/4. Invert and multiply, making it just one common fraction. And so when I do that, the 4 and the 2 are going to cancel. So I'm going to have 18 over 13. Is that correct? Okay, multiply by 4 over 13 here, and multiply by 4 over 13 here. These cancel. This goes to a 2, and now do you buy 18 over 13? Okay. My means I expected more. Now what? Oh, that's 4 over A. Helps if I write the A instead of a Z. An A. 4 over A. So what am I going to get here? Cross multiply. 18A is equal to 52 if you want to multiply. Our arithmetic is not doing so hot this morning. So 18A is equal to 52. And so I'm going to divide both sides by what? 18. Not quite. 3 times 18 is 54. Good estimate. 3 times 18 is 54, so it's close, but it's not there. Now, I can reduce that, correct? 26 over 9. So 26 over 9. 26 over 9 goes how many times? 2 times with what left over? 2 and 8 ninths? 2 and 8 ninths, right? 8 ninths is what forever? Eighths. Wow, that took a moment more than I thought. So 2.888888 forever. Or 2 and 8 ninths. Now my point is, you aren't getting hung up on the algebra. What are you getting hung up on? The arithmetic. And unfortunately, most of the problems in algebra are getting hung up on arithmetic. A moment of honesty. I love algebra. I translated for Sandra. It went something opposite that. But you will learn to love algebra. Okay, I agree that it's hard to translate and it's easy to like something you're doing well in. What is really the difficulty, I believe? Retention. You do the problem and then you haven't done enough of the problems, and so every time you see a new one, it is a learning curve. It's going back through again, and it gets tedious. So what do you do? Lots and lots of problems, like 20, 30, 40 problems, until it is automatic. I don't care what it is, folks, whether it's an algebra class, an arithmetic class, whether it's soccer, whether it's golf, tennis, you name it. How do you get good at it? Even if you're talented, you practice and repetition. At world-class levels, you just, the work ethic. And if you think of football, the people who were, you thought so gifted, and they worked at it with a work ethic that was unreal. It's been interesting to watch Tiger Woods come back into professional golf again after being out for nearly a year. In the first 2 tournaments, didn't put it together. And finally, this last weekend, won, starting way behind the pack in the last day. It doesn't come just talent, and he's talented as heck. Whether it was a Jerry Rice in San Francisco who in football was doing impossible things, but he had the greatest work ethic of nearly anybody in the team. Okay? Musicians, they make it look easy. They spend hours and hours getting to that point. And folks, that is, I believe, why the quiz grades aren't where they should be. You're doing the computerized problems. You are not walking into the quiz on a tutorial ready to play. You haven't practiced the problems. You've just been doing the ones. You're still in the learning curve. So again, practice them until they just come easily. Richie. Okay, the 52. 4 times 13, cross multiply. Okay? That wasn't off the topic. 2.88888 forever, or 2 and 8 ninths. Okay, any other questions in the homework? Good. I'm going to come back center. And I'll allow this to go back. So Michael, if you'd be kind enough to hand that back to Kim, I would appreciate it. So the problems that you're working in 7.5, some of them are more difficult than others. We've had one problem from this. I don't know just how far you've gone in this, but for the most part, the question comes of what units of measure do you use in your equivalence. And so I'm just going to look at a typical problem here and ask, what do you need to know? And then you tell me, again, the equivalence. Number 31, as we look at it in the screen. Okay, so this is number 31. A person from Russia claims that her mass is 55 kilograms. We want to know the weight in pounds. And I don't care for the moment what her weight is in pounds. But as we come off there, what equivalence did I ask you to memorize? Okay, 1 kilogram, 2.2 pounds. That's the one you use. Now, there are two given, but that's the one you hang your hat on. Let's go to a different problem. I had the problem and lost where it is. There we go. It's number 10. And by the way, there is no way under earth or above, say under heaven or above earth, I would do this problem from a practical point of view. Look what it asks you to do and think of the insanity. A family builds a 4-foot fence. Convert it to centimeters. Why? Maybe meters, but not centimeters. So the question, what did I ask you to memorize for this one? Coming off there now. What equivalence? 1 inch is what? No. Okay, you're having troubles. An inch is about between 2 knuckles on your finger. Just take your index finger and crook it like I'm doing there and go from the knuckle to the joint. That's about 1 inch. Now, run your pinky across there. How many pinkies go into that?
3.
Just under 3. 2.54. So 2.5 pinkies and a knuckle. So you got big knuckles. Sandra's saying it goes 3. Either she has a small pinky or a big knuckle. I don't know. But it's roughly 2.5. And I'm being a little much of a smart aleck. But the point is that gives you a conversion. So 1 and 2.54. Now, if I remember that, and Ernie, I'm going to the sideboard on this, if you would please. Will you first go to the document cam for me so I can get that set up? And let's just look at this one. And again, there are times when things are done just because they illustrate a point, not because there's any common sense provided. I see nothing gained, and somebody will probably tell me, yeah, but you should know that this is in centimeters. Number 10. I have a 4-foot fence. How many centimeters? No, just this is the question. How many centimeters? That's now the question. I want centimeters. And I'm only going to remember a minimal number of equivalences. So I'm going to take the knuckle and the pinky. So I have centimeters here, 2.54. And that's 1 inch. Okay, but I have feet, right? So what am I going to do? 12 inches. 1 foot. 4 feet. Not bad. Right? So feet and feet, inches and inches. So I have 2.54 times 12 times 4 centimeters. So this is 48 times 2.5. So that's 96 plus 24, where I have about 120 plus something. So I've got a lot of centimeters. No. 48 times 2.54. Okay, so we have 32, 43, 20. I have 16, 21, 10. I have 2, 9, 1, 1, 2. And I said about 120, and I'm supposed to be at 121.92 centimeters. Now, I can't ever think of somebody measuring that way. It's like saying, how many inches in the football field? If you run 100 yards, how many inches did you run? You can do it, but who cares? Okay, so some of these problems are going to be in that level. So don't get upset because it's asking for something that you'd not normally do, but it's to show you how you could do it if it was an important problem. Is there any difficulty with that? Okay, so we are saying that 1 inch we're taking at 2.54 centimeters, and we said that 1 kilogram is 2.2 pounds. What's the other one I gave you? Liters and quarts. What did I give? 1 liter is a what? No. Close. 1.05. It's a 5% above a quart. What is the 157? I just remember it as 5% plus. Those are the three. That should cover most of the games. Let's see. Let's go back to the document cam. Let's see if we can do the problems we're looking at there using these measurements. And I'm trying to keep it simple. Again, there's a thing called paucity. P-A-U-C-I-T-Y. Paucity. So P-A-U for pa and city. C-I-T-Y. Paucity. And the idea is to get by with as few words as you can. Well, I'm applying paucity to the number of formulas I have to memorize, the number of equivalences I have to memorize. These are ones that are not too familiar to you, but they will work. So, let's look at number 20. How many liters are in a half gallon of milk? So what are you going to do? You want liters, so you're going to use which of those three? Ernie, show me the three in the sideboard, please. So which of those three? Do you want to zoom in on those a little bit if you could? Bottom one would work, wouldn't it? So let's come back to the document cam. We wanted to know how many liters. So coming back to what I see up there, you would start with 1 liter over 1.057 quarts times 4 quarts equals 1 gallon times 1/2 gallon. Okay? This is one that's interesting, 28. Now again, the question on this one. You want to know how many grams in a 2.5 ounce serving of rice. I would be more interested in how many grains of rice in a 2.5 ounce serving. But what are you going to do? Which one of the three? Go back to the board. You could use kilograms, couldn't you? Let's see if we can set that one up. And my point is, you have learned how to do some pretty tough dimensional analysis problems. And I don't care in terms of what we're doing here. And I need to go back to the document, Cameron. Sorry about that. I should have told you what I wanted. I want this problem about how many grams in 2.5 ounces for rice. See, that ties together with my Jerry Rice comment. Nobody even said, ugh. Okay, no humor this morning. Okay, so I have 2.5 ounces and I want grams. So G-R-A-M-S, I'll write that out. And we're going to start with ounces, but what I have here, now we can come off there. I can go back to what? This one, because I know, now this is where you got to be careful, 1,000 grams is a what? 1 kilogram. And 1 kilogram is 2.2 pounds. And 1 pound is 16 ounces. And I have what? Coming back to the problem, 2.5 ounces. Now you say, well, what am I going to do with the decimal here? Not worry, because you're multiplying it by what? 1,000. So 1,000 times that means 2,500 over 2.2 times 16. I got everything I need there? And grams. I didn't say the problem's nice, but it's doable. Okay, yes? As opposed to regular ounces? Well, we have ounces. Okay, you have weight, right? So you have like 16 ounces in a pound, but then you have a fluid, which is 32 ounces in a quart, and those ounces don't match up. Okay? And so we're measuring two different things. One is technically, for us, weight. Looking at it as kilograms, it's mass. So to that extent, there's a slight difference. But in terms of volume, we just have, unfortunately, used the same notation. So you have ounces being used, liquid versus weight. Now, in an interesting way, we tie together the cc and the milliliter, right? So then you tie volume in terms of physical measurement with a liquid measure, because it's the amount of liquid that will go into 1 cubic centimeter. And we say that the kilogram is the weight of the water that will go into 1 liter, so you sort of standardize those. We don't have any standardization for weight and liquid measure in the American system, where we talk about ounces for weight and ounces for volume, and it's a little bit confusing because one's 16 and the other is 32. Okay? There's no way around that. Now, I'm not going to finish this off. My point is, this is a little bit long, but this, as a dimensional analysis problem for where you've been, isn't a biggie. And we did what? We kept with these three. Ernie, if we slide over a little bit, we've still kept with those. Let's go back to the document camp. Now, I'm not arguing that every single one of these can be done with those three, because if they do something with temperature, you're going to be what? You're going to have to go to our formula. But let's come back up to this one with a carpenter, with a 3/8 inch drill. And I want to convert it to millimeters. Well, what is your choice of the three I have up there? Going to the sideboard again, just with those three, Ernie, if you can zoom in on them. So I have a 3/8 inch drill bit, and I want to convert it to millimeters. Let's go to the sideboard. Which one? The first one. It has inches in it. And it's going to go to centimeters, and then I have to do what? Run centimeters to meters, and then meters to millimeters. Take it a step at a time. So if I look at this problem, let's finish out with this one. Let's come back, see if I can bring that down a little bit tighter. So we want this in millimeters. I think that's easy enough to read. So let's see what we can do. Again, the reminder, what do you start with? What you want at the end. Okay, so I'm going to start with millimeters, correct? So I've got millimeters. Okay, now I'm on my way, coming off there. What do I know about millimeters to meters? 1,000 of these little dimes, that's the thickness of a millimeter, is going to be 1 meter. Okay? Now, in terms of that, I could go to what? 1 meter is what? 100 centimeters. But 2.5 centimeters, 2.54 centimeters is 1 inch, and I have 3/8 of an inch. You can do 0.375 if you wanted. Now, as I look at this, first, all these other dimensions cancel, correct? Then the 100 goes into here, but I'll write it out so all the numbers are there, because you have been with problems looking much worse than this in the past. This isn't a biggie, and I'm going to give you a choice here. Now, this is where you think before you do. The old phrase, think before you jump kind of argument. This is in millimeters now. Your first reaction is what? Cancel that 100, cancel it there? I don't know about that. Because if I multiply 1,000 times 0.375, I get rid of that decimal. Whether that's good or not. So I'm going to have a 2.54 times 375 over what? 100. Now you might say, well, I don't like that. I like better 2.54 times 3.75. Okay. What's your rough estimate? This is close to 4. That would be 2.5. 2.5 times 4 is about 10, so I figure about 10. But you multiply it out and get your millimeters. I'm not so interested in what you do that last step. I'm interested in the fact that this doesn't blow you away and you say, hey, we've been there before. Okay? I'm out of time, even without a fire drill. Okay, so Ernie, I have no idea. We don't know who's playing on these songs, but have you got some idea what you're selecting and you're just blindly choosing? Okay, this is a blind choice. No pre-reference, so what do you have? Rock and roll. Okay, well, let's hear what it is.